Bismillahirrahmanirrahim. Assalamu alaikum. How are you, students? Today, our topic is about thermal methods of analysis, and the uh, course is luminescence spectroscopy and thermal analysis, and course code is CAM 4128. And in this course, we will discuss the chapter that is about thermal analysis. This is lecture number 10, and in thermal methods of analysis, in last time we already discussed about differential scanning calorimetry. So we will further discuss about differential scanning calorimetry or DSC in this lecture. Let's start. So main concepts or key contents that we will discuss in this lecture about differential scanning calorimetry and its instrumentation, as there are two types of instruments that could be uh, used in DSC. One is a power compensation DSC and other is heat flux DSC. We will discuss the difference between two, what is the main difference between two types, and then we will discuss about some sample pens and sample preparation that is needed for analysis. After that, we will discuss that how we can determine heat capacity, what is heat capacity, and how we can determine it by DSC. So, in differential scanning calorimetry or DSC, next we will discuss about its instrumentation and DSC analyzer. We already discussed about differential scanning calorimetry's principle and its introduction. So here we will discuss about instrumentation in next slides. So actually DSC analyzers can measure the energy changes that may occur if a sample is heated or cooled, or if it is held isothermally as a function of temperature at which changes may occur. So DSC analyzer actually measures the temperature difference that may occur when we heat our sample, or when if we cool it, or if its temperature is maintained constant. So we can get energy changes or heat changes that may occur between sample and reference. So it is noted as a function of temperature. At low temperature, which these changes may occur, DSC analyzer can analyze it. So these energy changes are heat changes enables the user to find and measure the transitions that may occur in sample, and they can also note the temperature where these transitions may occur. And so one can characterize the material for melting processes of that material and also for the measurement of glass transitions. One big advantage of DSC is that samples are very easily encapsulated, and mostly sometimes no very little preparation or no preparation is required for DSC samples, and they can be easily placed in DSC analyzer, so that measurements can be quickly and easily made, because there is no need to prepare a sample for DSC, differential thermal scanning calorimetry. So it can be readily placed in DSC analyzer, and it could be quickly measured or analyzed. So now we will discuss differential scanning calorimetry instrumentation, and the instrument is known as differential scanning calorimetry analyzer or DSC analyzer. Or so two basic types of DSC instruments are used. One type is power compensation DSC, and other is heat flux DSC. So next we will discuss detail of both and what are the difference between two types. First type of DSC instrument is power compensation DSC, and it was introduced in the early 1960s. So a sample holder that could be used in DSC, power compensation DSC, could be made up of platinum, or it could be made up of aluminum. So next part, that is and this is first part, sample holder, that we discuss in every thermal analytical methods. So in DSC, sample holder is made up of aluminum, or it is made up of platinum. So sensors that are used in power compensation DSC, that may be platinum resistance thermocouple, and for both reference band and sample band, two different sensors and heaters are attached with the sample and reference that can measure the heat flow difference between two. And the furnace is for both sample pan and reference pan. Two separate furnaces or furnace blocks are used. But in case of next type that we will discuss, heat flux DSC, and with that type, a single furnace block is used. But in power compensation DSC, two block furnaces are used. For example, there is a separate block furnace, and for reference there is a separate furnace block. So temperature controller, the part that control the temperature. So the working of temperature controller is to supply or to provide the differential thermal power to the heaters, and to maintain the temperature of sample and reference at programmed value. So as we already discussed that if there is a difference in temperature of a sample pan, it increases or decreases, then these temperature controller can control the uh, can give the specific program value that is needed, or that is have to withdraw from the sample pen, that is controlled by temperature controller. So in this figure you can see that the reference pen that is enclosed in a furnace block separately, and the other left side is a reference pen that is enclosed into furnace separately, and there are two thermocouples connected with both. One is connected with the sample pan, and other is connected with the reference pan. And there is a heater that is individual heater, and that are heaters that can provide heat, and the thermocouple or a thermocouple sensors which can detect the changes and heat flow or temperature. So other type is heat flux DSC, and in this type, sample and reference holders are made up of aluminum or platinum pans. The same pans could be used for power compensation DSC, and these aluminum or platinum pans are placed on constant wire. That is the difference between heat flux and compensation DSC. And sample and reference holders are next connected by a low resistance heat flow path. So sensor, next part is sensor. Sensors are thermocouples that are used in heat flux DSE. It could be made up of chromal, that is alloy, and it is made up of 90% nickel and 10% chromium. If you mix 90% nickel and 10% chromium, then you can get chromal alloy. Or it could be made up of Constantan area thermocouples. So Constantan is also alloy, and it is alloy of copper and nickel. And in this alloy, 45% nickel is mixed and 55% copper is mixed. And sometimes these sensors are made up of both the chromal and Constantan. And the next sensors can also be made up of aluminum alloy, that is alloy of approximately, it consists of 95% nickel, 2% manganese, and 2% aluminium, and 1% silicon is added to form aluminum. So, chromal aluminum, mixture of chromal and aluminum is also used as a sensor, as a thermocouple. So, thermocouple, what is thermocouple? It's actually a junction. It is connection between two different metals that produces a voltage due to temperature difference. So, a sensor could be made up of chromal, or it could be made up of constantan, or it could be a mixture of chromal or constantan if we need a differential heat flow. And it could be made up of only enamel, or it could be made up of chromal and enamel if mm, we need a sample temperature, we want to measure sample temperature. So furnace, the difference between heat flux and heat flux DSC and power compensation DSC is the difference of furnace here. And here in this case only one block of furnace is used for both reference and sample pan. In this figure you can see that sample pan and reference pan are placed in same block furnace. Here one part or one block of furnace is used, and both are put into this single furnace block. So temperature controller, and we already discussed that the function of temperature controller is that to control the temperature difference between sample and a reference, that is converted to differential thermal power, and this power is supplied to heaters that can maintain the temperature of the sample and reference at program value. जैसे हमने पहले बात की थी कि अगर सैंपल और रेफरेंस रेफरेंस जो है वो तो कांस्टेंट उस पर रहेगा, बट सैंपल पैन के अंदर हम उसको सैंपल डालते हैं, तो उस वजह से उसके जो टेम्परेचर डिफरेंस है सैंपल और रेफरेंस के दरमियान टेम्परेचर डिफरेंस आ जाता है। तो वो जो है टेम्परेचर कंट्रोलर जो है वो एक्चुअली उस जो भी टेम्परेचर डिफरेंशियल जो डिफरेंस आता है सैंपल और रेफरेंस के दरमियान उसको पावर में कन्वर्ट करता है और उसको भेजता है हीटर की तरफ, ताकि हीटर वो जो जितनी हीट रिक्वायर है या जितनी उससे ड्रॉ करनी है उस वैल्यू पे उसको ले आए, ताकि रेफरेंस और जो आपके पास सैंपल पैन है उनकी वैल्यूज़ दोनों की इक्वल हो जाए, जो दोनों की वैल्यूज़ क्या हो, कांस्टेंट हो। So sample pen and our sample holders are crucible, could be made up of different metals or different materials. So it could be uh, made up of aluminum and sometimes platinum metal. And these sometimes these pans have lid on it, and sometimes these are without lid. And this could be made up of aluminum in third picture you can see. And the fourth one is made up of nickel, and you can see that some could be made up of copper, and at the end you can see that here is a pan that is made up of quartz. So when you are putting your sample in the pan, then avoid to overfill the pan. that you can get the good results, and the material cannot be overflow from that pan. So mostly small sample masses are taken, and heating rate is mostly kept at we analyze our sample at low heating rates that can increase the resolution. When we are going to analyze any samples, though, the main and important step is sample preparation, then how we can prepare our sample. So we already discussed that the main advantage of DSE is that we don't need to prepare sample a lot, that no efforts are needed to prepare sample. It's easy to place in pan, and then we can directly put it into uh, crucible or pan. So first thing that we have to do for sample preparation or analysis is, first we have to accurately weigh our sample. That could be approximately from 3 to 20 milligrams. We can take from 3 to 20 milligram of sample. And we already discussed about sample pans or crucibles that could be made up of aluminum, or it could be made up of platinum, nickel. So we can use mostly we use that metals or that materials that which are inert, or which cannot react with our sample. So we should ensure that the sample we are using, it should not react with our sample pen. So several types of pens could be used for analysis. That could be open, or it could be airtight. So it depends on our sample that which kind of material we are going to analyze. So we select our pen according to that material. So if we are using one material for sample analysis, if we're using one pen that is made up of platinum, the same pen we should use for reference. So if sample and reference pen both should be made up of platinum if we are using sample pen that is made up of platinum. So and same arrangement of the sample material as sample and reference pans should be similar. It should be arranged in same manner. It should be similar to the contact with thermocouples or heaters, or it should be kept at the same position. So materials that we are adding, or sample that we are analyzing, it should completely cover the bottom of the pan, that to ensure the good thermal contact. So if we put our sample in the pan, it should completely cover the bottom of that sample holder. So it can, that sample or that analyte can get good thermal contact with the pan. So if we are going to determine heat capacity by DSC analyzer, so DSC plot could be used to determine heat capacity. For example, suppose you have a polymer that is being heated by a DSC analyzer. So there is one is a sample pan in which you have added polymer, and other is a reference pan. When you start heating two pans, the computer will plot the difference in heat output of the two heaters against temperature. Temperature will be taken at x-axis, and heat flow will be taken at y-axis. So that is plot of heat. The plot that we get is a plot of heat absorbed by the polymer against temperature. So if heat will be absorbed, this plot will look like this as given here. It will be straight line. So next is specific. We are using, if we are using DSC analyzer, so we can determine specific heat from it. So the next topic is the determination of specific heat or heat capacity. So specific heat, or we can also say it's heat capacity, and it is represented by Cp. So specific heat or heat capacity of material can be determined quantitatively by using DSC, and it is designated as a CP, as we can say that the values are obtained at constant pressure. So the accuracy that we can get, it depends upon the instruments and the method we are using for determination of heat capacity or specific heat. So generally, if we practically talk about in our practical routine, the traditional standard test methods provide a fairly rapid method for determination of CP, and many manufacturers provide softwares specifically that are designed to comply with that methods. So what is heat flow that we recorded or we measure on the y-axis? Heat flow is heat. It is represented by Q, and we can say that heat flow is the heat supplied per unit time. We can say that heat divided by time. We can represent it as Q over T. Q is heat and T is time. So heat flow is a heat supplied by per unit time, whereas heating rate is the temperature difference per unit time. So we can write equation for it as for heating rate, that temperature increase over time is the heating rate, and you can show it this equation as, you can write this equation as delta T over T. So delta T is a temperature increase, and we take it as a per unit time, so we will divide this delta T over small t. So this is equal to heating rate. So if we divide heat flow, we divide it by heating rate, where we in previous slide we discussed that heat flow is Q over T, that is heat divided by time per unit time, and if we divide this heat flow by heating rate, and heating rate is delta T over T. Delta T is increase in temperature and T is time. So increase in temperature per unit time, it will be equal to heat capacity or CP. So here you can see that we can say that finally here you divide this Q over T, that is heat flow, and you divide it by delta T over small t, that is heating rate. This small t and small t will be cancelled, and you will get the final equation Q over delta T. So this heat flow, this heat and difference in temperature will be equal to Cp or heat capacity. So the equation that we get is heat supplied divided by temperature increase, and this is called heat capacity. Or we can also define or describe heat capacity as, like, when a certain amount of heat is transferred to the sample, its temperature increases by a certain amount, and the amount of heat it takes to get a certain temperature increase is called heat capacity or Cp, and it could be seen from DSC plot. सो हीट कैपेसिटी को हम कह सकते हैं कि एक स्पेसिफिक अमाउंट हीट की जो कि सैंपल को ट्रांसफ़र हुई है, और जिसकी वजह से सैंपल का जब वो हीट ट्रांसफ़र हुई है तो उसकी वजह से जो सैंपल का टेम्परेचर एक स्पेसिफिक अमाउंट तक इंक्रीज़ हुआ है, और जो अमाउंट ऑफ हीट जो कि टेम्परेचर को इंक्रीज़ करने के लिए जो कि अमाउंट ऑफ हीट जो उसने ली है सैंपल ने, तो उस जो टेम्परेचर इंक्रीज जो है उसको हम क्या कहते हैं, हीट कैपेसिटी कहते हैं। सो जितनी अमाउंट उसने उसमें टेम्परेचर को इंक्रीज करने के लिए हीट की, सो उसको हम हीट कैपेसिटी से डिफाइन करते हैं। So in next lecture we will discuss about DSC plot or DSC curves, and also about DSC calibration and information that we can get from DSC curve or plot. For further information, you can consult this book, and you can also find some other sources online. So you know that today we discuss instrumentation of DSC, and here we discuss two types of DSC analyzer. One was power compensation, differential scanning calorimetry analyzer, and other was heat flux DSC. So what you have to do, you have to differentiate between power compensation DSC and heat flux DSC. What are the main differences between these two types? And I hope so that you will understand and that you got my points in this lecture. If you have any questions or any if you cannot understand anything, you can ask me. That's all. Thank you.